Okay, great.
Let's do this. So, Erdine, do you record?
Yeah, it's recording now.
Thank you. Good morning, everyone. It is my pleasure today to welcome our speaker. Our speaker is Alex Lechman. He's an associate professor in physics at the Holland Institute of Technology in Israel. Alex obtained his PhD in 2003 from Technion in Israel. Then he had a first postdoc on molecular photophysics at CNRS in Orsay in France. I didn't know that. I didn't realize, Alex, that you had a
That we
French
can speak. That we
research
can speak
period.
French. Yeah.
That's very nice. And then he had another postdoc on space environment materials at Sorek Nuclear Research Center in Israel. In 2007, Alex joined the physics department of HIT as senior academic staff member. His main research interests are in nanoparticles characterization, functionalization, and their applications in energy-related subjects like hydrogen storage and production, solar cells, sensors, and more. Alex published more than 50 papers in peer-reviewed journals and is very active in a number of international research networks, including Netpore. And we are very happy today to have Alex talking about multi-layer tungsten disulfide nanoparticles for energy-related application and as breath sensors. It's a nice program. Thanks, Alex. This is
Yeah.
yours.
Thank you very much. Just I want to ask because I cannot see the screen who participates. Are there my colleagues from Croatia and Iceland in the listeners? If yes, that part of the work is what I'm going to present is our joint work with the group of Andrea Gajovic from Zagreb, Croatia, who is also MC member of this network of Netpore, and also the group from Reykjavik University. They also joined Netpore a couple of years ago. So if they are here then they're very welcome. I'm happy to see you. Otherwise, as Fred just presented, I will talk about various energy applications. So when preparing this webinar, I considered either to present one subject in a very, very extensive way, or several applications, and I decided that I will present several applications because most of the audience they are not experts in this kind of nanoparticles that I'm working with. So to give some more interest in their different applications, I chose to go into to a number of subjects which related to their multi-layer porous nature of these nanoparticles to talk about. And as you will see, much of this work was performed within cost action, this cost action, and also some previous cost action within my collaboration during STSM and after that. So just a few words about my institution. So we are Holon Institute of Technology, which is very close to Tel Aviv. You even cannot see the city of Holon because we're just 5 kilometers from Tel Aviv. There are streets that one side is Tel Aviv, another is Holon. So we have a campus of about 6,000 students, of which about 1,000 are graduate students and the others are undergraduates. So if you come to us, we have now nice dorms also for staff exchange rooms. So I hope the situation will be better in a short time and we can fully resume our activities. I mean the international activities, because otherwise our activities are quite full. Okay, I will go to my talk. So these are the main subjects of my talk. So first, I will talk about WS2 tungsten disulfide nanotubes as catalyst for hydrogen evolution reaction, so for production of hydrogen. This work was performed in collaboration of my colleagues, both from here, from HIT, and from another university in Israel, Ariel University, who are electrochemists. So I was responsible for nanoparticles and their treatment. They are electrochemists for electrochemical measurements. So the funding was the joint fund of HIT and Ariel. Then I will talk about the same type of nanoparticles as a medium for hydrogen storage. For their use in perovskite solar cells. And in relation to this, I will extend to their doping with gallium to improve their electrical conductivity. And finally, very briefly, I will talk about another application which is not directly related to energy, but using them in silicon nanowires to improve their breeze sensing capabilities, which was performed with Reykjavik University, and I will extend on this at the end of my talk. So, just what is common for all parts of my talk are the materials that I'm working. These are generally WS2 tungsten disulfide nanoparticles, which are very different from the same WS2, which is well known for 100 years as nearly amorphous particle that you can find them in different, for example, oils, additives, and so on. When we are talking about nanoparticles, we're talking about two types of nanoparticles. The first one, they are called inorganic fullerene or fullerene-like nanoparticles. So, frankly speaking, they are more like onion-like particles than not fullerenes. But anyway, they are nearly circle particles. They range from 100 to 350 nanometers. So some call them giant nanoparticles. They have multi-layer structure, a lot of pores, a lot of defects on the surface, for good and for bad. And also they have a presence of hollow core in their structure, and this is due to the difference between the specific gravity of WS2 and WO3, which is the precursor for their synthesis. Another type of nanoparticles, which I will talk much more than about fullerenes, are nanotubes of WS2. So again, the nanotubes of WS2 that I'm working, they are multi-layer, multi-wall nanotubes, not single wall, but multi-wall nanotubes. They are generally about 50 to 100 nanometers wide and can be as long as 20 microns, even some longer. They have open ends, so we can introduce species inside also from their ends. And again, they have defects, they have pores, so which made the possibility for other atoms or other species penetration. So about the synthesis process that we're doing in the neighboring lab of my colleague Alazak here in HIT. This is a schematics of the process. In all cases, we start with oxide, tungsten oxide, which also means that at the end of the process, we have some residuals of oxide. And then there is a gradual, quite complicated process of reduction. First, we produce by special conditions kind of nanowire of tungsten oxide. And then there is a reduction process from oxide to sulfide with hydrogen and H2S gases at high temperature, going always from outside to inside. And this is why sometimes in the inside, the tube is thicker than the interlayer distance. So we have some space sometimes inside until we get this WS2 nanotube, and you can see the TEM image of this real nanotube. Now I will go to the first application, the using of these WS2 nanotubes for hydrogen evolution reaction, so namely for production of hydrogen. As you know, hydrogen evolution reaction is electrolysis of water, and generally it's performed with platinum electrodes. The platinum electrodes are required as catalysts because otherwise the process is very, very slow. On the other hand, platinum is quite expensive, and with the time there could be some degradation. So we're always in looking for another type of materials which is cheaper than platinum, but have similar or the same catalytic properties. So we suggested to use to cover the electrodes with the tungsten disulfide nanotubes, and indeed, when we during the initial process, the results were not so good as I will show you later, until we induce some another treatment, which is radio frequency cold plasma treatment with either argon or hydrogen or both gases. So in this plasma treatment, we use quite a low pressure of up to 1 torr, between 0.5 to 2 torrs, namely, with power. Here it's written up to 1 kilowatts, but we never use more than 300 watts. And here the frequency and magnetic field. In such case, the temperature is still about room temperature, so we don't heat the samples. So this is cold plasma. And then there are either argon or hydrogen. I will tell you later why we're using these gases for the plasma. And after this plasma treatment, we have very dramatic changes and the enhancement of the properties of these WS2 nanoparticles as catalysts. So I will start from the end. So as I have just told, there is some residual oxygen from the synthesis process. And in addition, there is also absorption of water. So generally, this water it's possible to remove by annealing in a vacuum in the same plasma chamber to 150 to 200 degrees in half an hour, 1 hour. But for some reason, in several experiments, we did not do this. And it turned that it's very beneficial to leave this small amount of water on the sample surface, on WS2 surface, before performing the plasma treatment. As it turned that because of plasma, we have very minor oxidation of the first layers, nearly between the pores of the initial layers of the nanotubes. So you can see here the schematics of the process. And by such a way, using the plasma, we induce high-density surface defects, and then they perform much better as electrocatalysts than defect-free WS2. Defect-free WS2 means the WS2 nanoparticles before plasma treatment. So we suggested that this low power RF plasma treatment increases the number of disordered sites at the surface, and we will prove this experimentally, and produce atom vacancies, so significantly enhancing energy conversion performance due to the more effective interaction of plasma activated sites with the nanoparticle surface. So why we use these two types of plasma? Sometimes just one type of plasma, and sometimes one after another, but never simultaneously. So hydrogen plasma, sometimes we use the deuterium plasma for measurements to be sure that the result comes from plasma and not from any other process, because there is high permeation of hydrogen combined with the retention of the plasma properties along the sample width or thickness. So hydrogen plasma and hydrogen excited molecules by plasma, they go much inside of the layers of the nanoparticles. While argon plasma, it has no chemical effect, but just high impact energy and superior cleaning capability. So by argon plasma, we also clean all the impurities from the atmosphere and so on. So these were our predictions, and then I'm going to results. First of all, TM shows that following plasma, there is no change in the structure. We still have quite perfect nanotube. There's an electron diffraction pattern, so this is okay. But where are the changes? There are some chemical changes. So we can observe by FTIR, for example, that there is formation of some bonds with oxygen, sulfur, and tungsten oxygen. So this supports our assumption about the formation of surface defects and substitution of very individual sulfur atoms with oxygen atoms. So we don't produce layers of oxide, but just individual on the individual sites. For XRD, again, the structure is preserved. The structure of the nanotubes is preserved. But then we observed a peak which is related to WO3.H2O. So we have some kind of passivation of this oxide with water molecules which were residuals from the atmosphere. So which residuals because we did not perform any annealing. And in the case of micro Raman, in addition to these two peaks which are characteristic of WS2 nanoparticles, so we still have perfect WS2 nanotubes, we have also in this region structures related to oxides. Even going to much deeper characterization by XPS, where we can see peaks related again to the hydrate phase of water, this water passivating phase, and we can also detect that while tungsten oxide peak is intense in pristine samples, but after plasma, its intensity goes down. So, and we can also we also notice the reductive nature of hydrogen or deuterium and so on. So this is about chemical characterization, but the most important was EPR, electron paramagnetic resonance. Because generally WS2 nanotubes, they have not so much defects or free radicals to show any signal in EPR. And indeed, when we measured pristine nanoparticles, there was no signal. But after treatment of these nanoparticles by plasma, and either deuterium plasma or argon plasma or both type of plasma, then we obtained very high EPR signal, about 20 times more than it was for pristine nanoparticles. And even at low temperature of 140 K, we obtained the signal which proved that we have free radical presence and not something else, and not some kind of vibration excitation. So the fact that it's measured at such a low temperature for sure confirms that we have still free radicals and defects even after some time after performing the plasma process, because we to do the CPR we had to take the samples from the plasma and then to move it to the EPR machine for the measurements. So now going to electrochemistry, because this was the purpose of these experiments. So this was done performed by our colleagues from Ariel University. So there are several types of measurements. The most important is the first one, linear sweep voltammetry, which assesses the excess potential needed for the sample to initiate HER. The lower potential you have, the better is the process. Of course, at a specific current density, we use the current density, the standard current density of 10 amps. 10 milliamps for square centimeter. And as you can see, when we have tungsten disulfide nanotubes before plasma treatment, this overpotential is quite high. It's not so useful for HER reaction. It's about half volt. But after plasma treatment, we can go right and right until the overpotential is about 246 millivolts, which is improvement of 2 types. Later, I will show our ideas and our experiments to reduce it even more. But now concentrating on these WS2 nanotubes treated by plasma, we also performed some other measurements. For example, CV cyclic voltammetry, which shows that for the similar mass loadings, the plasma treated sample show more current density, so they have better catalyst performance. The impedance, electrochemical impedance spectrometry also confirmed that there is a dramatic decrease in charge transfer resistance for double plasma treated samples. And also the TFL plots, the slope, when there is a smaller slope, and as in the case of plasma treated samples, here that indicates a faster kinetic process, which means that the catalyst can achieve the required current at a lower potential, which is always beneficial. So we suggested this kind of mechanism. Again, I'm not electrochemist, so we should discuss this with my colleagues from Ariel, but they consider that it's electrosorption of a solvated proton, kind of Volmer reaction, and then recombination of the adsorbed hydrogen, excited hydrogen, and another solvated proton to form the molecular hydrogen within this hydrogen evolution reaction reactor. Of course, we performed another test. For example, we also measured the stability of so produced composites, and for at least 12 hours, there is very negligible degradation of the electrodes. So we proved by such a case that RF plasma treatment activated previously inert surface due to formation of defects, as we proved by EPR, and then these defects they serve as active sites for electrocatalytic reaction. Before going to another part, we still decided to compare our nanoparticles, plasma-treated nanoparticles, with other materials, nanomaterials. Most of them based on WS2 or WS with the other compounds. And then we observed that our results are still not the best, because as I have just told you, we obtained 264 over potential, while in other materials it was slightly lower, though their preparation and the process was much more complicated than in our case. So then we consider how can we further improve the results. And then our solution was, in addition to the plasma, to use carbon nanodots driven coatings of these nanotubes in the following schematical mode. So first we coat the nanotubes with a layer of these carbon nanodots. So we choose this type of materials because they are zero band gap material. So we expected that it will generally lower the band gap. WS2 nanotubes, by the way, they have not so narrow band gap of about 1.9 to 2 eV, unless they are doped. So after this, there was kind of a oxidation process to thin down the carbon layer, and then there was a reannealing to remove this oxide layer. And then we compared again the overpotential and of course all other measurements that I'm not showing here for differently treated samples. So when we have just this carbon coating and no plasma, indeed there is a reduction of the overpotential from the 567, which is for untreated nanotubes, to already better than in the case of just plasma, 172 millivolts. But when we perform also argon plasma, and then we also did this with hydrogen plasma and both plasma, though the results are about the same as just for argon plasma, then we go down even to 95 millivolts. So 95 millivolts is 3 times better than we obtained just plasma and without this carbon coating. So we are now working on the explanation. So now just in the preparation about the paper, so I'm not going into much details about this process and the mechanism, but the results are very, very promising and quite exciting. So I would like briefly to summarize this part of my talk. So we illustrated that low energy RF plasma treatment indeed improves catalytic properties of WS2 nanoparticles, and with the first carbon coating, carbon nanodot coating, we obtain results which are very, very close to platinum electrodes, but hopefully which their cost is much lower and the stability is quite high. So we're considering that the mechanisms related to pores and defects produced by the plasma that serve as active sites for the reaction. So this is about this type of the research. Now I will move to another part, which was performed even before this, the previous one. We try to use WS2 nanotubes and fullerene-like nanoparticles for hydrogen storage. This was because they are multi-layer. They have pores and defects on their surface, so we can see that hydrogen can go inside and can be safely stored in these materials, and they easily released. So most of this work was performed was started about 10 years ago, and then we continued it for about 7 years. And there are several papers that we published. Even it was within cost action, not this one, of course, but the cost action on solid state hydrogen storage, which was active from 2012 till 2016. So for this type of process, we used several kinds of hydrogenation methods. So the easiest one and the most popular is just high pressure hydrogen. So just exposed to the hydrogen at high pressure. It could be done either room or high temperature or low temperature. And here you can see the weight percent of hydrogen. As you can see, the weight percent of hydrogen for the high pressure molecular hydrogen are very, very small. Though I have to tell you that because the molecular weight of hydrogen is just 2, and the molecular weight of WS2 is 247, this very small weight percent are still very high atomic percent. But anyway, it's not enough, though. By using intermediate low temperatures, we improved the situation. Then we decided that molecular hydrogen as is not good, and so we have to do some kind of excitation. And the excitation was either RF plasma. From this research, we later came to other applications when we're using RF plasma, and also microwave plasma. So here you can see the weight percent. With microwave plasma, we obtained about 1.2, even in some cases 1.28%. The problem with microwave plasma, it was too aggressive. So sometimes there was a decomposition of the nanoparticles, and these people who performed plasma for us even could smell some H2S from the nanoparticles. They were not very happy about this. So we concentrated about RF plasma because it was stable, room temperature, no destruction of the nanoparticles, and so on, as I have just presented you in our previous applications. So we would like to explain these results and to know what kind of hydrogen absorption we have, either chemisorption, physisorption, and so on. For this reason, we communicated with our colleagues from Spain, the theoreticians, and they're specialists in DFT. DFT, in particular, related to hydrogen and nanoparticles. Julio Alonso and Jose Ignacio Martinez. Julio Alonso from Valladolid University, Jose Ignacio Martinez, he's now in Madrid. And they calculated by DFT different structures from pristine nanoparticles or nanotubes to hydrogen adsorption. And then they calculated the adsorption energy. And in the case that adsorption energy is positive, it means that the adsorption process is favorable. If it's negative, it's not so favorable. So they started their calculation with just physisorption and different types of hydrogen configuration on top of WS2, either nanotubes or nanoparticles. I'm not showing you all the results and all the structures, but just to have an impression. And for hydrogen coverage in fractions of monolayer. And then you can see that in this case, the energy is positive, so the adsorption is favorable. But then we noticed one additional effect, which later proved to be very important for us. When we have this hydrogen adsorption, which is energetically favorable, we also have some minor increase in the interlayer distance between WS2 layers, because, as you know, it's a multi-layer structure, from just 6.13 angstroms for pristine nanotubes to 621 for the hydrogen adsorbed nanotubes. You can consider it's very minor, and there is no sense, but later we proved that it saves us a lot of energy. Later, we also proved that hydrogen can be absorbed in several layers, in multi-layers, and still the absorption process is quite favorable. So we can have 2 or 3 layers of hydrogen. This shows why we have quite high hydrogen percentage on the nanotubes than it could be in the case of single monolayer. On the other case, we were quite disappointed that this calculation showed that in the case of intercalation of hydrogen, so we consider that most of hydrogen will be intercalated, then in this case, the process is very non-favorable. We should get a negative energy, and this was quite disappointing. But then, using the experimental TEM, we obtained this expansion of the interlayer distance in some local sites, which is well predicted by the DFT. But DFT says that this extension is so energetically consuming that it will never happen. But it happens probably because of pores, because of defects, because of open ends, and so on, or because of we are using not just molecular hydrogen for absorption, but plasma excitation. And also, most of the energy consumed is consumed to increase the interlayer distance by this 0.1 angstroms. But this interlayer distance already increased in the hydrogen absorption with no cost. So although energetically not favorable, but we do have some intercalation or many intercalation of hydrogen. I'm not showing you here the calculations for atomic hydrogen, because for atomic hydrogen you have to somehow to dissociate hydrogen. There is some plasma dissociation, but it's the percentage of atomic hydrogen dissociated by RF plasma is very, very low. Otherwise, you would have the bottle of atomic hydrogen, the process will be very, very favorable, and probably we could have a lot of hydrogen, but I don't have such a bottle. We should have a kind of atomizer to bring the hydrogen to dissociation, which consumes a lot of energy. So from various hydrogenation method, we proved that the plasma activation is essential. So we continued with RF plasma. Experimentally, we observed only physisorption. We performed Raman measurements and so on, and we never observed any chemisorption. So we never observed any bonding between a hydrogen and sulfur, or hydrogen with tungsten. It's not possible. And there is, of course, also hydrogen diffusion, which is so some kind of low temperatures are beneficial, while the intercalation of hydrogen molecules is not favorable, but it occurs because of the defects mainly produced by plasma originally presented, and then we have this hydrogen inside the molecules, and then we also proved that it can be quite easily released at 40-50 degrees, but it's quite stable at room temperature. Anyway, we did not achieve the percentage of 5 or 6%, which is requested by industry, so we're still not suggesting to use these nanotubes as hydrogen storage medium, but this case of simple structures and calculations. On the other hand, another energy-related application of WS2 nanoparticles, and in future also molybdenum S2 nanoparticles, is to integrate them with perovskite solar cells to enhance their performance and stability. For example, hybrid halide perovskite transition metal disulfides nanocomposites. This research is performed with our colleagues from Croatia, from Zagreb, Andrea Gajovic, who I knew just within this cost-action. So this is a real collaboration that this cost-action promoted. So, and in addition to STSM, we have now the bilateral grant of Israel-Croatia Ministries of Science for 3 years until the end of 2026. So in this research, we aim to overcome the instability of halide perovskite and improve their parameters, but developing the novel formaldinium halide perovskites with incorporated either WS2 or later, when we have the sufficient quantities, molybdenum S2 nanotubes for use as photon absorption layer. The challenge is that WS2 nanotubes, as they have not sufficient conductivity, and plasma treatment does not improve the conductivity. And the proposed solution is doping. So doping can be used by the chemically, for example, with rhenium, but it's very, very complicated process of, and you should change the synthesis procedure, or by ion beams. So we suggested the doping with gallium. So I will briefly move to the gallium doping, and then I come later to this research of perovskites. So this gallium implantation was performed using focused ion beams, and this was in collaboration with the group from Sabancı University, then Meltem Sezen from Sabancı University. At the time now she moved to Holland, to Netherlands, and the theoretical calculations were performed also with the same colleagues from Spain, Julio Alonso and Jose Ignacio Martinez. And we used gallium 30 keV beam in a feed machine, and then we measured the concentrations of gallium by EDS in the scanning electron microscope. It was quite interesting to us, and we did not have any explanation at that time that in the case of pristine nanotubes, the atomic concentration of gallium was at the limit of detection, just 0.1 atomic percent, and at the ion dose that did not produce any substantial damage to the nanotubes. Because if we increase the ion dose, then we have heating and melting of the nanotubes, so it's not good. So we should maintain the ion dose to be quite low to keep the nanotubes in their pristine structure. We just tried this the same process with previously plasma hydrogenated nanotubes, and to our surprise, because we did not expect this, the atomic concentration raised 3 to 4 times, which is quite sufficient for doping. We published this result that I will just present you in a moment, just less than 1 year in small. So our interpretation was related to expanded interlayer spacing because of hydrogen plasma treatment that we observed when we considered these nanotubes as hydrogen storage media, which I just talked about this several minutes ago. So first of all, you can see that indeed when you use high ion dose, let's say in the range of 10 to 16, 10 to 17 per square centimeter, we have change in the structure, we have kind of melting of nanotubes, so not something that we wanted to proceed. In the case of the dose of 10 to 15, the structure is preserved. When we implanted gallium by FIB, first of all, we observed the chemical change by micro Raman. So still, again, these two strong peaks are characteristic of WS2. So as soon as we have, as long as we have, they are quite strong, it means that the structure is still as it was before, the good crystalline structure. For example, in this case, you can see that there is a reduction of these peaks because of structure change at high dose. But also we have these small peaks which are related to gallium. Again, we should remember that the gallium concentration is quite small. So, and also the cross-section for Raman is also quite small, and this gallium was related to this kind of structures as from the literature. So this is kind of proof of gallium implantation. And then there are calculations. First of all, if we have just pristine nanotubes which are not treated by hydrogen plasma, then implanting gallium, according to calculation, should induce interlayer expansion from 6.15 to 6.65 angstroms, and then we can produce up to 0.7 atomic percent of gallium with the theoretical limit. So we cannot have any more than this 0.69 atomic percent. This requires a lot of energy because though implantation energetically favorable, but there is a very high energy barrier to overcome in the case of non-hydrogenated nanoparticles, because we need to expand the interlayer distance. In the case of hydrogenated or previously hydrogenated nanoparticle, we already have this expansion, either because of just adsorption or because of intercalation of hydrogen. Remember that in the case of intercalation of hydrogen, the interlayer distance, because of this hydrogen, can extend up to 8 or 8.5 angstroms. In the average case, 7.68 angstroms. In this case, we don't have any barrier. So when we start with already hydrogenated WS2, then large interlayer distance means then implantation is facilitated. And here you can see the diagrams for the case of pristine nanoparticles, not hydrogenated and hydrogenated, and you can observe that we absolutely removed the implantation barrier. I'm not showing you here, but we also performed later the electrical conductivity measurements, and this gallium implanted nanoparticles. After first treatment, of course, we have to anneal the nanoparticles to make gallium evenly distribute in the nanoparticle structure. The electrical conductivity goes down. So we consider that this gallium doping, this research is not has not been completed yet, but the electrical conductivity goes down. So to conclude this part, we can see that our findings open a gate to introduce other species after hydrogen treatment, after hydrogen plasma treatment. We can introduce other species with the objective to functionalize further nanoparticles or similar nanomaterials by modifying their original properties. So after resolving this issue of electrical conductivity and doping, I'm coming back to the perovskite solar cells. This research we're completing now the first year, which was very, very difficult, and so we don't have a lot of results for this perovskite solar cell with WS2, but already the results that we have, they are quite promising. Here you can see just schematics, not necessarily related to specific types of perovskite that we are working. This is just a kind of illustration. And for example, we, or let's say our colleagues, or the group of Andrea Gajovic in Zagreb, they prepared the mixture of the Fa perovskites, formaldinium perovskites, with different concentrations of WS2 nanoparticles. Here you can see the concentration. They measured the transmittance, and they see that there is some increase in the absorbance for the high concentration of nanoparticles. On the other hand, they also produce kind of device to measure the conductivity for different type of concentrations. They measured the conductivity of the films, these films of the mixture of perovskites with nanoparticles, and then they obtained that, for example, for the concentration of 0.1 milligram per milliliter of WS2 nanoparticles in the perovskite mixture, the conductivity increases very sharply, more than 2 orders of magnitude. Yeah. And then when we performed the SEM along with scratch tests, first of all, we see that the surface morphology is the same, so they promising thin film formation for the use in electrical devices. But when we use scratch test to see what goes underneath, then we can see that WS2 nanoparticles behave like an armature, so so protecting layer for the perovskite crystals, which crystallize around WS2 nanostructures. And so this anti-WS2 armature inside the perovskite film influences the overall conductivity of the film and enhance the charge extraction of the electrons. And this is why we already obtained this increase of conductivity, and it also can be attributed to single crystal structure of WS2 and their nature. So these are just initial results. I visited this group within my STSM, funded by Netpore cost action in late October. So we have quite, and now we are summarizing some more measurements and we hope to publish them within several months. And finally, in a couple of minutes, I will talk about the very different type of research related to WS2 nanoparticles. But again, it was initiated within STSM by Netpore about 2 years ago in Reykjavik University. It's now also funded by Erasmus Plus grants between HIT and Reykjavik University scientific visits. So the group headed by Andrei Manulescu and Muhammad Taha Sultan and Haldor from Reykjavik University School of Physics or Physics Department. Sorry if I'm naming not correctly the department. So the idea is to use WS2 nanotubes as materials for toxic gas sensing, for example, NH3 or NO2, both for medical reasons and for environmental reasons. Now most of the sensors are metal oxide semiconductors like SNO2, zinc oxide, titanium oxide, tungsten oxide, and so on. All of them, they measure changes in electrical resistance. The problem with them is high operating temperatures, 200 to 400 degrees, which means also high power consumption, long-term response drift, and limited sensitivity. And if you would like to use them as a medical device for breath test, then it's quite difficult to operate them at this kind of temperatures near people who just breathe, and it's quite a problem. So they are not so suitable, less suitable for wearable breath analysis sensors or device operating at room temperature. So it's we're always looking for different type of sensor materials, and we're turning to nanomaterials based sensors. So the group at the Reykjavik, they previously, and they're still working on silicon nanowires. Silicon nanowire, they have excellent chemical activity, large surface area, they are functional at room temperature. They are quite effective for detecting a trace amount of gases and suitable for real-time breath monitoring, for example, in sleep apnea diagnostics. If you add to these nanotubes, for example, carbon nanotubes or WS2 nanotubes, we have even better characteristic. Carbon nanotubes, they have hollow structures, high aspect ratio, so they have increased gas absorption sensitivity, enhancement to alcohol, NH3 and O2 as a breath test. Probably alcohol, not all of us are quite happy with this development. Some, consumed before driving and so on. WS2 nanotubes, they can provide added value because of their chemical resistivity. So they are very, very inert, so they are not destroyed at the atmosphere or even at relatively high temperatures. If doped, they have quite narrow band gap, but even if not doped, their band gap is okay. Good carrier mobility, high surface to volume ratio, so they can be used as chemi-resistive gas sensing, so they are not supposed to be destroyed neither by NH3, not by NO2. And they have got good gas sensing performance at room temperature. And this is because charge transfer between gas molecules and the material surface. Just to show you some results, some more recent results performed mostly in Reykjavik. Here you can see these nanotubes. They are grown with the help of silver nanoparticles. These are not coated nanotubes. These are nanotubes, silicon nanowires coated with either carbon nanotubes or WS2 nanotubes. And all measurements are performed based on their resistivity change. Here, the electrical sim for the measurements. And it was performed either for normal breathing, for rapid breathing, and for deep breathing according to the standards. And the response time, here the explanation what's the response time, has been measured for different types of nanotubes, of nanowires. PANI means polyaniline. Polyaniline with carbon nanotubes, just carbon nanotubes, and WS2 nanotubes. As you can see, in nearly all cases, the response time for breathing in all regimes, or most regimes, for WS2 nanotubes was beneficial, was shorter than in the case of all other additives. So here you can see this measurements of resistivity for breathing of normal people for different regimes. This is a derivative, and the spin-coated WS2 structures demonstrate a higher rate of change over time, suggesting greater response to breath profile variations than just silicon nanotubes. And they show baseline drift implying reduced stability compared to WS2 coated structures. So WS2 coated structures provide a great advantage from this point of view. And this is my last slide. So some explanation. So we consider that there is a depletion layer band charge transport in the case of this P-type silicon nanowires and N-type WS2, even when it's not doped. So we consider that sensing function relies on the ability to act as a charge acceptor or donor. So WS2, they exhibit strong absorption properties for water molecules, because remember, breath test is always performed at the atmosphere. So, and water absorption is quite strong on the nanotubes. Sometimes we don't want this, but for the breath testing, it's proved to be beneficial. So there is interaction. This interaction changes the resistivity of WS2, which is naturally N-type, due to either N-doping or P-doping, and then the absorbed water donates electrons to the material, enhancing its resistance. And this is followed by charge transfer, and then this water absorption reduces the overall conductivity of this hybrid structure, and in such a case, we obtained much better sensing capabilities of silicon nanowires speed coated with WS2 nanostructures than the case of just bare silicon nanowires. Again, a lot of work is yet to be done. We are now also in the preparation of the paper with results, with some experiments yet to be completed. And so now I think it's time to complete my talk, and thank you for your attention.
Thank you very much, Alex, for this nice presentation. It's a very impressive amount of experimental and theoretical work, and it's very interesting. We have a few minutes for question, so please don't hesitate to raise your hand or just start speaking.
Yeah, I cannot hear you because if I cannot see you, because if I go away, it will be a problem me to come back to the presentation in the case of yeah. So just.
Okay. But do you hear me now?
Yeah. I'm okay. Yeah.
Okay, very nice.
So, I just cannot see the participants. Yeah.
Yeah. Okay. So I may have a. Oh, is someone speaking? Excuse me. Okay, so I may have a question. It's just going back to your very last comment on the adsorbed water that donates electron to the material. And so in there, is it a good thing or a bad thing?
Yeah, it's a good thing for it's a good thing for breath testing. It's a bad thing in the case you should have good conductivity. So it's a bad thing, for example, for perovskite solar cells, but it's good thing for bridge test. So you see that the same issue can be positive or negative for different type of application. Yeah. For here,
Yeah,
because here we need in the breast testing we need to increase the resistivity and the resistivity response. So in this case, when there is water absorption on the WS2, it increases the resistivity, and then it's the sensitivity of the testing is also of sensing is also enhanced.
yeah, this is a very interesting feature that you have with your material because you can play with it. And I was wondering if you could just envisage to chemically modify the surface with a few molecules to make it more hydrophilic or hydrophobic and play with this
Yes,
trap
yes,
in the.
we observe this issue. For example, when we treat the nanotubes with hydrogen plasma, the previously annealed nanotubes with hydrogen plasma. So first we remove water, and then we treat with hydrogen plasma. Then we obtain the surface very hydrophobic. So even when we expose these materials to atmosphere, then the water absorption is very, very small. We approved this by TJ in the work related to hydrogen storage. If we don't do this, we just prepare the nanotubes and expose them to atmosphere, they are very hydrophilic.
Okay. Thank you, Alex. It's really interesting and very so many applications that you have and
Yeah, these are
nice
just part of applications, but I decided to concentrate on these results. And again, I'm very thankful to Cost Action, this action, and another one that they really allowed us first. Some of the collaboration we initiated within the Cost, and some were promoted within the scientific visits, these short-term scientific missions that really they promoted, and they gave us the possibility to initiate or to promote the research when we did not have another sufficient funding for some subjects.
Yeah. I understand.
Thank
Thanks a lot for Netpore, by the way. It's great. So we have a question in the chat from Mustafa Muradov. Mustafa, you want to talk, or should I ask the question?
Just ask, because I cannot, if I go to chat, I
Okay. Yeah.
lose this this
So
slide.
Mustafa said, "Thank you for your great speech. The question is about doped carbon material. Which method do you use for it?"
Carbon material.
The doped carbon materials, yeah.
I'm not sure that I talked about doped carbon materials because I think the only carbon materials I talked were here. In the case of carbon nanodots that we used for hydrogen evolution, but we don't need any doping because it's graphene-like, and naturally the band gap of graphene or graphite is nearly zero. So we did not use any doping here. Sorry. Yeah. There was some doping. It was nitrogen doped. Sorry, it was end-doped carbon. Yeah, and the material, I think the end doping was either by phosphorus or by sulfur. I cannot tell you now exactly which kind of atoms they used, but as far as I know, because it was used by our colleagues from Ariel, they prepared these films. But as far as I know, for carbon, the N-type doping can be either by phosphorus or by sulfur, because nitrogen is very deep line. They have the deep line level, so this doping by nitrogen is not very effective. While p doping is by boron.
Okay. Thank you,
Yeah.
Alex. Thank you very much. Any other question for Alex today? Okay, so if not, then we can thank you, Alex, again for your very nice presentation, and thank you
Thank you.
very much for your
And
participation.
thank you very much for allowing me to present our
Oh,
results.
you're very
Yeah.
welcome, and thank you for participating to
And
this
see you
webinar.
again on the Netpore activities. Yeah.
Thank you very much, and thank you all for your presence today at the webinar session of Netpore, and I wish you a great day, and hope to see you in a month. Thank you very much.
Thank you.
Bye, Alex. Have a great day. Thanks a lot.
Thank you.